Okay, good afternoon, everybody. You're very welcome to this session on data science in mental health, opportunities and challenges. My name is Breda Cullen. I'm based at the University of Glasgow, and I'm just going to kick off the session with a very short introduction to what data science is and how that's relevant to mental health research. So there's a number of different definitions out there for what data science is. This one at the top of the slide here is very broad. It says it's probably fair to describe data science as generating new knowledge from real-world data. And the second definition on the slide here is a little bit more technical, a bit more specific. So here we see that data science is the extraction of knowledge from high-volume data sets by use of computing science and statistics. So high volume data sets, that refers to the fact that there's a lot of data. Sometimes people use the term big data, and it can be high volume in the sense that the data set contains data from a lot of people, or it can be high volume in the sense that there are a lot of data points collected for different people, or a mixture of the two. So in terms of the computational approaches that are relevant in data science, as you can see on the left of the image here, this involves techniques such as data linkage and the use of high-performance computing clusters for parallel computing. And then, on the other hand, we have the statistical methodologies, and this includes different ways of handling high-dimensional data, different approaches to statistical analysis, and in particular, the use of techniques such as machine learning, and you're going to hear some examples of that in our session today. I really like this infographic about data science, which was in this paper by Russ and colleagues from a couple of years ago. And I think what this illustrates really nicely is that no matter what kind of mental health research you can think of, there is a role for data science in it. So as you can hopefully see from the diagram here, data science can be used in all sorts of ways to explore mental health across the lifespan, to understand the causes of mental illness, to look at preventability and modifiable risk factors, to improve detection and screening, to help us develop new treatments and improve existing treatments, to help us find better ways to support people in living well with a mental health condition, and to drive improvements in health and social care. We're really fortunate here in Scotland and in the rest of the UK to have some excellent resources and initiatives that support mental health data science. So here are just a few examples. Well, we have Mental Health Data Science Scotland, which is a collaboration of 3 Scottish universities. We also have various initiatives that support infrastructure underpinning data science research, and that includes SHARE, which a lot of you will have heard of at previous NRS events, and HDR UK, which supports infrastructure and also supports funding for early career researchers. We have MQ, which is the funding charity, and they have a very active data science group and a lot of great resources on their website that I would encourage you to explore. And finally, on this slide, I wanted to highlight the catalogue of mental health measures, which is an absolutely brilliant web resource that was put together by Louise Arnaud and colleagues at King's College London. And this is essentially an index of more than 30 different cohorts and data sets used for data science research in mental health in the UK, and you can explore that by entering mental health keywords or the names of measures, and that will then tell you the data sets that are out there which you as a researcher might be interested in making use of, and information about how to get access. The other really interesting thing about mental health data science and data science in general is the way in which it spans research data and routine data. So research data is data that we would think of as being gathered in a sort of traditional research way, where a project plan is put together and data are gathered with particular research questions in mind. Whereas routine data has been gathered for another reason, and that might be clinical data or administrative data, for example. And data science research makes use of a whole spectrum of different kinds of data sets that span this range from research data to routine data. And our speakers today are going to be giving you lots of great examples that I think exemplify the spectrum between those 2 different types of data sources. So here is the plan for the rest of the session, and I just want to let you know that the way that you can put questions in for us to answer later is by preferably using the session chat box that you should be able to see on the right-hand side of your screen. So you're very welcome to type questions in there as we go along, and we'll do our best to answer as many as possible in the panel discussion at 2:10. If for any reason you can't use the chat, there is also the option to ask to share your audio and video, and that would mean that you could speak live in the panel discussion by clicking on the blue button. But if you're able to put your question in the chat, that would be really helpful for us. You should be able to see through all of our presentations the slides and also the camera image from the speaker. If the slide appears to be too small, there's a way that you can make that larger by double clicking on the slide image at your end as an audience member, and hopefully that will make it clearer for you. So without further ado, I'm going to invite Dr. Heather Walley and Dr. Mark Adams to present to us on the Straddle project.
Thanks, Brita. See my slides okay? Yep. So I'm Mark Adams, and together with Heather Walley, we're both from the University of Edinburgh. Just to introduce our project, which is called the Straddle Project, and this is a longitudinal study of resilience and depression. So we sort of have, so longitudinally, this extends both forward and backward in time. The core of this project is the Generation Scotland sample, and this was a sample of families in Scotland who were recruited through their GP, who came in for a clinical visit as well as genotyping. Since then, we've gotten data linkage, both members of Generation Scotland who were part of two Scottish birth cohorts, the Children of the 1950s in Aberdeen, and the Walker cohort, which is based in Dundee, as well as longitudinal record linkage data from the NHS. And the Straddle project was a recontact that took place sort of around 2015, 2016, where individuals were brought in for an additional blood draw, additional imaging data, or introduction of imaging data, and then a reassessment of mental health. And finally, just this year, we've instituted this project that Danny Smith talked about earlier called COVID Life, where we're just following up these individuals over time. So this is an overview of the kind of data that we have. So it's extremely comprehensive. People came in for a clinical visit and got a whole bunch of health measurements, as well as doing questionnaires of cognition, personality, and mental health. And the thing that's good about these kind of data sets is they're extremely rich. So we are able to look at the associations between different kinds of traits that wasn't possible before. So for example, looking at comorbidity between physical and mental health, and being able to tie that in prospectively to people's health records. Here's a list of all of the mental health phenotypes again. So it's a little bit, because this is a population sample, we're very focused on common mental health traits. So things like anxiety and depression. But I think, again, what makes this really unique, particularly for collecting data during the lockdown period, is we have longitudinal information. So we're not just getting a cross-section of what people's mental health is like during lockdown. We know what they were like before that, so we could sort of see how their baseline mental health is influencing how they're coping with current situations. And then just to say a little bit about the genetic data. So we sort of have a pedigree of all these people. We know who the brothers and sisters and parents and children and aunts and uncles. We even have some families with up to four generations. They've all been genotyped, so we know how they're not just related to each other through a pedigree, but how they're more distantly related to each other. And recently, we've also started collecting methylation data. So this is information on modifiable changes to the genome that affects gene expression. So sort of what we're able to do with this kind of data is tease apart things that are normally confounded in a lot of studies, like genetic and environmental sources of similarity between relatives. So siblings grow up in the same household, but they also share DNA, and we're just able to tease those kinds of things apart. And then on the left or on the right here, I've just got an example of how we're using this data in combination with record linkage data. So looking at self-reported antidepressant usage and seeing if that affects the methylation signal at all, and then confirming those self-reports with the actual prescriptions that these people have been receiving. So next I'll turn over to Heather to describe the neuroimaging sample in our study.
So hello, can you hear me okay?
Yeah.
Great. So so thanks to Mark for the introduction and to Frida for the invitation to speak today. So I'm going to focus on the straddle sample that has neuroimaging data. And I'll give a short description of the imaging data that we've collected, give a few examples of some ongoing studies, and then finish with a slide outlining data access for those of you in the audience that are interested. So the total imaging sample size was just over 1,000 participants, 1,067. And as Mark mentioned, they were recruited from Generation Scotland with a preference for those who were part of longitudinal birth cohort studies, like the Aberdeen Children of the 1950s and the Walker birth cohort. And there are further details in the Wellcome Open Research paper listed at the bottom. And they were split roughly equally across 2 scanning sites in Aberdeen and Dundee. Mark, could you switch the slides? Thank you. So the imaging measures we used were designed to capture brain structure, function, and connectivity that was relevant to depression. And we conducted structural imaging to derive measures of subcortical volumes, cortical metrics, and white matter hyperintensities. We've also included diffusion-weighted imaging to look at white matter microstructure and function imaging. So we've used 2 tasks within this protocol. The first is an implicit facial emotion processing fear faces task, and the second is a reward task. And I can go into more details if people are interested. And we also have a resting state scan as well. And in general, we followed processing of the data along the lines of protocols that are used in other large-scale data resources and consortia like Enigma and UK Biobank in order to kind of facilitate comparison. What we're doing in addition to those protocols is also deriving structural and functional connectomes shown on the right-hand side. Can we go to the next slide? Thanks. So this slide is a summary of some ongoing analysis, drawing together different types of data that Mark's described. So the imaging measures, but some biosampling and some epigenetic data. And in this study, we were interested in looking at the association between peripheral information and brain structure and mood. So exploring the hypothesis that depression could have inflammatory origins. And for this, we've used a blood-based biomarker, CRP, which is C-reactive protein, which is thought to be a good proxy for acute inflammation. And we've also looked at more longitudinal chronic measures of CRP through looking at the epigenetic data, linking up with Riccardo Marioni's group. Excuse me. And what we found was that the acute inflammation, which is shown in the upper plot, it was significantly associated with only one neuroimaging feature, which was entorhinal cortex thickness, which was decreased. But it had significant associations with measures of current acute mood symptoms, including somatic features like general interest and energy levels. And in contrast to the acute measures, the epigenetic score, which is of more chronic inflammation exposure, had more widespread and more significant effects on brain structure, but no association with the acute symptoms. So perhaps indicating that the more chronic exposure of inflammatory markers over time is related to what would be expected to be slower changing neural features rather than potentially transient acute symptoms. Can we go to the next slide? So one of our other studies is looking at the ability and accuracy of machine learning methods to classify depression into case control status using structural imaging data. And for this, we've successfully achieved about a 75% accuracy into cases and controls for the straddle sample. But what we couldn't do was replicate this in the larger UK Biobank sample. So, and in fact, the larger the sample size, the lower the accuracy seen in the right-hand side of the figure. And these challenges, these demonstrate the challenges of this type of approach then the importance of replication. And the next slide. So finally, I'd just like to mention another collaboration involving Generation Scotland, now not restricted to those in Straddle, but across all of Scotland. And here we're linking routine clinical neuroradiology assessments with electronic healthcare data for all individuals within Generation Scotland, with the hope of identifying novel links between common physical and neurological conditions with mental health conditions. This is in collaboration with Will Whiteley and the clinical NLP group here at Edinburgh, who've derived methods to text mine text mine features within the neuroradiology reports. And this has been a fairly heroic undertaking, not just in terms of the interpretation of the neuroradiology reports using text-based machine learning methods, but also some of the governance issues and complexities involved in anonymization, again highlighting some of the challenges of this type of data science. Next slide. So I'd just like to finish by acknowledging all the researchers involved. This is actually a picture of some of the participants who have been scanned as part of Straddle and proudly holding up pictures of their brains. And just the final slide, Mark. Thank you very much. So this is just how you can access the data if that's of interest. And thank you for listening.
Fantastic. Thank you very much indeed, Heather and Mark. That was excellent. Any questions that folk have about Straddle, please put them in the chat and we'll have a chance to talk about those later. So I'm now delighted to welcome Dr. Sam Layton from the University of Glasgow, who is going to tell us about prediction modelling in psychosis.
Right, just going to go back to the start. I take it you can hear me okay? Yes. Thank you very much, Frida, for inviting me to speak today. I'm going to talk about developing biologically relevant prediction models for individual patients with first episode psychosis using machine learning. This is part of a CSO clinical academic fellowship, which I have been awarded, and I've been supervised by Professor Jonathan Kavanagh at Glasgow, Dr. Simon Rogers, who's in computing here, and Dr. Rajiv Krishnadas, who's a clinician who also has an interest in first episode psychosis research. So just in case people don't know, psychosis is a mental illness which is characterized by hearing voices, muddled thoughts, and false beliefs. It is associated with a huge morbidity and indeed mortality. Only about 4 in 10 people reach a full functional and symptomatic recovery. We know that certain factors like deprivation and education level, pre-morbid adjustment are associated with a poor outcome at a group level. However, we currently struggle to predict outcomes at an individual level. So this is where prediction modeling comes in. So prediction modeling via machine learning has the potential to revolutionize medicine by allowing us to predict individual outcomes at an individual level. It has been successfully employed clinically in other areas of medicine. So you may or may not be aware of the QRisk tool, which is a tool which predicts cardiovascular risk. And based on this score, your GP will make a treatment decision. If your score in this clinical prediction tool is shows that you're more than 10% likely to get a heart attack or stroke in the next 10 years, then your GP will decide that you need to be put on a medicine to lower your cholesterol, a statin. And this is really the basis of precision medicine, making individualized decisions using data about the patients. So in the NHS in Glasgow, we're very lucky to have a first episode psychosis service called Esteem. And this is some research which was carried out by Professor Gumley a few years ago now, which looked at the patients within our service with first episode of psychosis and followed them up for a year to try and work out basically who was going to do well and who was going to do badly and what their characteristics were. And we found that of the patients with the first episode of psychosis, by a year, just over half of people had recovered and just under half of people were still treatment resistant. But we really couldn't tell who was going to do well and who was going to do badly at the baseline. I'm now going to talk about a study which I've been involved in, which uses two large data sets from the NHS in England. So this looks at the Eden data set, which is over 1,000 patients with first episode psychosis followed up for over a year in 14 sites, and the Outlook data set, which is 399 patients with first episode psychosis followed up for a year in 11 different sites. And you might recall from the previous talk that often when you build a prediction model in your development sample, you find that it performs very well in the data that you use to develop it, but actually it doesn't externally validate. So it's very important you have a second data set which you can replicate your models in to make sure that they actually externally validate and are generalizable models, not just for your own clinical study. What we were looking at here was symptom remission. So clinicians are fairly simple folk, and we just want to know if people are going to get better. So we decided upon looking at symptom remission as an outcome. Symptom remission is defined as a score of less than or equal to 3 on 7 different positive and negative symptom scale items for a period of 6 months. Now, I'm not intending you to really see this slide other than to say that there was a lot of data which is collected. So in the 1,000 patients, well over hundreds of different data items were collected at lots of different data points. And after going through these with clinicians and using expert knowledge, we still ended up at 95 different variables at baseline. So it was a lot of different variables, and how can we make sense of these different variables to build a prediction model? So this is where machine learning comes in, and the particular machine learning method that I use is a relatively simple one. It's called regularized regression. In particular, I've been using lasso regression. What this does is it helps you to select the important features from your data science, from your data, using a data science driven approach rather than arbitrarily picking them or doing or perhaps doing individual significance testing on the different variables. It considers them all together in a multivariable way, and you end up with a model which has far less features, less predictor variables, and is quite understandable and explainable. So that's lasso regression. So we ended up with a model on the Eden data set, which performed pretty well on external validation. So we tested this model on the Outlook data set, a completely different set of patients in different centers at a different period of time. And the model that we built had an area under the curve of about 72%. So basically, it gets things right about 72% of the time, which is pretty good considering where we are, because there's not really any prediction models at the moment. And in terms of the model, it incorporated the education level, duration of untreated psychosis, premorbid adjustment, hallucinations and thought disorder, insight, and deprivation as well. So we ended up with a model that performed well in an external data set. Made a wee clinical tool, which is on the internet, and you can put in your different variables and you end up with a probability of remission. And the idea for my PhD thesis, just very briefly at the end, is that we want to see how these models that we've built in retrospective data sets perform well. Do they perform well prospectively in a real world clinical setting? So can I take this model that I built on this retrospective set of data from the NHS in England and apply it clinically in the NHS in Glasgow, and can we make treatment decisions based on the outcomes? Can I improve the performance of the model? Because at the moment it's just clinical variables and demographic variables. There's no biological relevant disease markers. So can I add things like peripheral inflammatory bloods or MRS glutamate, which are plausibly related to outcome in psychosis, and can the model be improved? And finally, the model that I built at the moment is a static model. It's only predicting outcome at 1 year from baseline. Can we incorporate dynamic variables, things that change over time, like response to treatment, to build a model that dynamically updates? So the kind of translation of this is, again, just reiterating, we built a model using big data, and it seems to perform pretty well externally in a different sample. Can we apply the model in a clinical setting? Can we use this model to predict and inform the clinical needs for our patients? So if you predict someone's going to do poorly at a year, can we meaningfully intervene to change that trajectory? And this approach in my PhD, I think, brings together big data, computer science, and psychological medicine to try and solve a real-world clinical problem. So thank you very much, and I'll take questions at the end.
Excellent. Thank you so much, Sam. That was brilliant. As Sam said, please put your questions for him in the chat and we'll discuss those at the panel discussion. Thanks again, Sam. So we're next going to be joined by Dr. Mike Fleming from the University of Glasgow, and he's going to be presenting on linkage of health and education data for mental health research. Thanks, Mike. Over to you whenever you're ready.
Hi there, can you see my slides okay?
So I'm not seeing your slides up on screen yet.
Is there a button at the bottom for me to share?
So in your Chrome window, you should see the share icon next to the mic. Yeah, that's it coming up.
That's it. Okay.
That's it. Excellent, thank you.
Right, thanks, Beda. Okay, so I'm going to talk about work I've been doing looking at educational and health outcomes of children who have physical, mental and neurodevelopmental conditions. Now, obviously for today, I'll focus on the latter two. Try and get my slides to move across. So the reason this is of interest is because the determinants of health expand beyond just the health sector. We know that education can impact health directly by things like health promotions around healthier living, but also can impact it indirectly, because if you have a better education at school, then it sets you up for life in terms of better prospects, increased prosperity and improved health and well-being. But there's of course many factors that can influence how likely you are to have that initial good education, and one of those is chronic ill health, be it physical or mental. Now, we know that specific drugs are prescribed for particular conditions. Examples here are insulin for diabetes, inhalers for asthma. The ones I want to focus on again today is CNS stimulants prescribed for ADHD, and also antidepressants, which can be prescribed for depression, but also OCD and anxiety. So we're trying to find out which children are treated for those conditions. We can then look into comparing educational and health outcomes for those children versus their peers, and these are the types of outcomes that I was interested in. So how I went about this is as follows. In Scotland, we've got a very good population-wide health and education data. The education data that I used was 5 years worth of data from the Scottish Pupil Census. So that covers all children attending schools in Scotland, primary and secondary schools. It has a wealth of demographic data on those children, but importantly, it also has information on whether these children are receiving additional support, special educational needs for things like autism, learning disability, mental health, and I'll come back to that in the future slides. We also have a wealth of other information in terms of attendances at school, exclusions, exam results, what's happened to those children after they leave school, and these are all linked into the census using Scottish Candidate Number, which is like a unique pupil identifier where you can identify records relating to the same pupil. Of course, in Scotland, we've also got the CAI number. So in terms of health data, we've got the CAI number, which is records relating to the same patient. And of course, that's not on education data. So to link the two, we have to use probabilistic matching. And we can do that using pupil identifiers, such as date of birth, sex, and postcode. And once we've linked the pupil data to the CAI register, we can then use that CAI number to match, using exact matching, onto a number of different health data sets. So the ones that I was interested in was national prescribing data. Again, in Scotland, we have very good health data across the population wide. Prescribing gives us information on all medications prescribed and dispensed in the community in Scotland. So I could see which children were receiving the medications of interest. And then, as well as educational outcomes, we can follow those kids up in terms of hospitalisations and deaths. And we can adjust for important confounders by linking back to retrospective maternity records as well to look at birth factors. So I just want to focus on this. This is just to show the cohort size that we were dealing with. So over 2.7 million school records pertaining to around 750,000 school children passing through the education system over that 5-year period. And over that time, we managed to identify about 7,500 children receiving ADHD medication and around 5,500 children receiving antidepressants. So a large cohort. Now here we've got our outcomes of interest, which are down here. So 5 educational outcomes of interest and 2 health outcomes. And here we have our chronic conditions of interest. Now I'll blank out obviously the physical conditions, or at least try to, but I noticed my, oh, there it is there. So blank this out, and we can see here the effect sizes for children with treated for ADHD and children treated for depression, possibly anxiety or OCD as well. Essentially, those children are receiving antidepressants. And what we see is the effect sizes here are all above 1 and all highly significant, with the exception of the bottom one here. So essentially, for children that are receiving, have much poorer outcomes compared to their peers. So more absences at school, more exclusions from school, more additional support needs, poorer exam results, increased unemployment after leaving school, and they're also hospitalised more readily and have increased mortality as well. And it's a very similar picture for children with ADHD. I won't go into too much more detail than that because of the lack of time. But although I've blanked out the physical conditions, it is also important to take those into account, because what we do find is that children with other conditions such as diabetes, asthma and epilepsy also tend to have higher incidence of mental health conditions and vice versa. Oops, apologies. I'm still getting used to this new system. So what I do want to talk about however, is neurodevelopmental multimorbidity. Again, what we tend to see is children that have conditions such as ADHD or depression, they tend to have other conditions as well. We wanted to focus on neurodevelopmental multimorbidity, and we class that as 2 or more of any of the following conditions. So ADHD, depression, autism, and intellectual disability. And again, as before, we wanted to look to see what their educational and health outcomes were. And I'll just talk about the educational outcomes in this next slide. Again, here we see a similar linkage diagram to before. What's important here is that we can use this information. Previously, we used this as an outcome, but we can use the fact that we have information on additional support needs as a method of ascertainment. So for children that are attending school and have any additional support needs related to intellectual disability or autism, that is flagged up. So we can essentially tell which kids have those conditions. And in addition to the prescribing data, we can also obviously, as I said before, tell which children are receiving medications for ADHD and depression. So that allowed us to start looking at neurodevelopmental multimorbidity. Here we can see, just in terms of the prevalence of children with any one of those conditions, higher prevalence in boys versus girls, higher prevalence in terms of deprivation quintiles, so more deprived children that are more likely to have one of those conditions. And again, even starker when you look at the 2 or more conditions. So of those children that have 2 or more conditions, 80% of them are boys and 20% girls. And again, more in the more deprived categories. This next one here is really just to show the most commonly occurring conditions here, so intellectual disability and autism. I just also want to flag up that with the exception of depression, all of the conditions were more prevalent in boys. So that's autism, ADHD and intellectual disability. And again, we're more likely to see multimorbid conditions amongst boys compared to girls. Now, this is looking at the same educational outcomes as before, but again, this is looking at children with one of those conditions or children with 2 or more of those conditions. So again, looking at absence, exclusion, poor attainment and unemployment. And again, what we see is that children who have one of those conditions compared to their peers have poorer outcomes, and children who have 2 or more of those conditions compared to their peers also have poorer outcomes. But what we see is that there's a kind of dose response effect here. So the effect size becomes even larger. So that, for example, children who have one of those conditions have an almost 4-fold increased risk of poor attainment. That rises to a 12-fold risk if they have 2 or more of those conditions. So a very detrimental effect on those children. And just to finish off here, what I want to show here, I'm not expecting to go through this, I just want to highlight some of those effect sizes, because what we see is when we look at each of those conditions on their own and each of the pairwise combinations of those conditions, and look at the impact on absenteeism, which I'm doing here. We see that anytime depression comes into play, it has a big impact on the effect size. ADHD. So this next one is looking at the likelihood of being excluded from school. And this is looking at all the different combinations of singular conditions and various combinations of comorbidities. And again, what we see here is that every time ADHD comes into the mix, the effect size rises quite a lot in terms of the impact on exclusion. So it seems here that ADHD is a very powerful driver of school exclusion. This disappeared, but I think I'm running out of time. And so what we'll just do is, to finish off this last slide, I want to just draw your attention to some of the publications. These are the ones on ADHD, depression and neurodevelopmental multimorbidity, which have recently been published. And if you're interested as well, there's some ones that have been published on some of the physical conditions as well. And happy to take questions. Thank you.
Great. Excellent. Thank you very much indeed. Any questions for Mike, please fire them into the chat window for us. And we've been joined by Professor Sue Fletcher-Watson from the University of Edinburgh. And Sue is going to, first of all, tell us about evidence-based guidelines for best practice in mental health data science. And then all of the speakers will come back in and Sue will lead our panel discussion. So over to you, Sue.
Thanks. Perfect. Yes, so I'm talking about some work that was led by my wonderful postdoc colleague, Dr. Lizzie Kirkham, who's pictured here in the corner of the slide. And we've been looking at stakeholder-informed guidelines for mental health data science. So it's just important to flag that I think what we're particularly interested in here is guidelines for the use of routine data where participants have inadvertently contributed their data as part of the health record, for example, and have not been in a position to give informed consent for its use. And it's really important that we work with these kinds of data, as we've heard from some of the talks already today, because they can allow us to address problems in mental health research, challenges in mental health research, like, for example, dropout from studies, failure to recruit people from particular kinds of backgrounds, and just issues with kind of power and, you know, the power that we need for the sort of modelling that we've heard about a bit today. So we want to make sure that the voices of people who have lived experience of mental illness are heard in that process, even when it's not about sort of signing a consent form. So what did we do? So we're particularly interested in the kind of specific issues that apply when applying data science to mental health. So this is why we felt we needed guidelines specifically for mental health research, and we can't just use the kind of existing generic data science guidelines that exist around kind of good research practice. So when we're thinking about mental health, of course, we all know that there's a huge amount of stigma associated with mental health conditions, and that can mean that there are kind of particularly severe consequences if, for example, someone was inadvertently identified from a combination of variables in an otherwise anonymous data set. Mental health data involves a lot of qualitative information, such as notes taken by a therapist or a psychiatrist. And we also know that people with lived experience of mental illness tend to have kind of lower trust in service providers and lower satisfaction with service providers. And that may extend to then a lack of faith in the kind of research establishment. We also know from our own survey, UK-wide survey, that people with mental illness are less likely to be willing to share their health data. And everyone, regardless of their health experiences, is less willing to share mental health data than physical health data. So what we did was a Delphi study. We recruited 30 people who all had lived experience of mental illness and knowledge of data science. So they were experts on two fronts. They understand the scientific research context, and they also bring their personal experience of mental illness. And a Delphi study is a particularly powerful methodology for working quite intensively, but with a small expert group, to derive some kind of notion of best practice. So it was particularly useful for these purposes. This is a busy slide, but I will talk you through it. Here on the right, we have the full final checklist, which has 14 items on it. I'm not going to take you through every item. Obviously, I don't have time, and you certainly can't read them. It's divided into 2 columns. One is about best practice that we can apply today, right away, and one is about best practice that we can apply in the future. And the items are also grouped into themes: transparency, anonymity, security, and community, just to make it a bit easier for people to use. So very briefly, before I finish, I'm just going to highlight a few of the contrasts between the recommendations for now and the recommendations for the future, because I think they're really interesting challenges for us as researchers and practitioners in this space. So some of the changes, like this one, are looking for the application of new kind of systems, new governance and oversight. So while now we might be able to have a transparent process for responding to withdrawal requests, on the whole, we don't really have a system for any kind of independent arbitration in that situation. While now we have a lot of rules that we can apply to make sure that we don't accidentally disclose people's identity through combinations of data, it was really interesting to us that the stakeholders who engaged with this were looking for kind of a bit more freedom here and a bit more of a principles-based approach rather than a rules-based approach. And similarly, they were really keen that we should develop systems for secure remote access to data, not just in designated spaces, as a part of a kind of democratization of the process of access to mental health data. And finally, I think unsurprisingly, but very importantly, our community, our group of experts, were not just reflecting that it's important that we understand the context in which data were collected and what that means for the interpretations we're placing on it, but also that we should become part of the solution and make a commitment as a research community to reducing mental health stigma and to science communication. You can download the checklist at the Methods website. The link's there on the slide. I can post it in the chat as well. And that I'm going to stop there so that we can move on to your questions. Thank you. Great,
thank you, Sue. It's incredibly important work. I'm sure everybody in the audience will see the power of work that's gone into that and the importance of the different issues that you tackled there. So I'm just going to invite all of our speakers to come back and join us for the panel. It'll just give us a moment to get everybody back in. And then, Sue, you've probably made a note of some questions that had been in the chat through the talks, and I'll keep an eye out for further questions that appear as we go on.
Yeah, I have done. I mean, so I've made a note of some questions, and as Frida says, please do start to post more. I'm getting a bit of echo. I think maybe we should mute if we're not speaking, just so we don't get that. Sorry, everyone. But before we go into that, I'm going to be selfish, and I'm just interested to know whether any of the panel had any kind of comments on this checklist. It is hot off the press, so I'm aware that not everyone will have had a chance to look through it. But I'm particularly curious about anything that people think would be challenging to implement or anything that people felt was surprising. So if anyone wants to kind of wave their hand and make an attempt at that, that would be great. And in the meantime, I encourage the audience to post in the chat as well. Yeah, Frida, thank you.
I was really pleased to see in the guidelines that there was particular attention paid to the use of qualitative data. So that would be things like open-ended text data from people's medical records. And although the methodology is progressing in leaps and bounds for the analysis of this kind of data, the challenge is the anonymization of it, because your best practice guidelines are saying that we should be trying to be open in our sharing of data. And compared to sharing quantitative data, I can see this being a really big challenge, is anonymizing qualitative data at scale. Anybody who's tried to anonymise qualitative data, even on a small scale, I think would see the level of human judgment that probably needs to go into that. And I'm really curious to see how the field progresses in terms of how this can be done at scale or automated. I don't know if any of the others on the panel have more experience on that. Heather, you alluded to these issues when you were talking about Straddle. I don't know whether sharing the sort of open-ended data is something that you've looked into.
Well, certainly for the wider study looking at linking your radiology reports, the anonymisation has been a real tricky step. And this is, I mean, it's not qualitative, it's a structured report. So I can imagine that taking that to a more qualitative description is much more complex. Yeah, so I can only sympathise, I'm afraid. Yes.
I think you're completely right, though, Breda, and I think that my biggest hope is for advances in how we can use and create synthetic data as a form of kind of masking and creating anonymity. I think there's potential there, and I hope that funders will invest in that kind of methodological and infrastructure development to allow us to kind of expand what we're doing while maintaining the trust of the community. I don't know if anyone else has comments on that theme, or I can go to the first question that we've got. We've got a couple of questions for Sam. Oh, Mark's unmuted, I think.
Yeah, I'll just build a little bit off what you said. Just the sort of the idea of synthetic data. So it actually might be kind of interesting in a text mining approach. I don't know if people have seen this sort of deep, it's called deep dreaming, where you get a machine learning algorithm to sort of create an image of what it thinks it sees, and that actually teaches you something about what patterns are being picked up on. So in these kind of approaches, it might be interesting to sort of generate text from these machine learning models to see what is the computer reading from either from these radiology reports or from free text that people are entering. And I guess maybe just one more comment about the free text is just one sort of tricky ethical issue with free text is if a participant discloses something to you that you actually need to follow up on, like suicide intention and things like that, it can be very tricky from a investigator's perspective to have that kind of data.
Thanks, Mark. That's great. Right, I can see the questions are building up in the chat. At Sam on behalf of questioners who posted a little while ago. So one was asking Sam just generally for more detail about your model, and there was also a specific question about your choice to use lasso regression since the original variables were kind of clinically recommended or selected. I wondered if you wanted to comment on those.
Yes, I would like to. I'll take the second question first. So in terms of lasso regression, we did from over 100 end up with 95 variables. However, you can do sample size calculations for building prediction models, and there's a paper in the BMJ by Riley et al. And the sample size requirement was such that needed 15 events per predictor, and with 95 we had 5 events per predictor variable. So we were at very high risk of building a model which was going to be very high in variance and not very useful and not externally validate. So we made a decision, we couldn't clinically reduce the number of variables further, so we made a decision to use statistical methods and use lasso regression. Whether or not that's the right decision, I'm not sure. All I can say is that the model does externally validate. And in terms of more detail about the model, there's just a lot of different variables in the logistic regression model. The main things that seem to come up again and again are things like premorbid adjustment scores and some particular PANS items like hallucinations and conceptual disorganization. But this is a piece of work which is under review at the BJ site, so hopefully it should be coming out soon and you can find all about the model then.
Thanks, Sam. That's fantastic. So I'm going to switch on to Mike now. There's a question here about multimorbidity in neurodevelopmental conditions and whether that can be explained by higher risk of adversity. And the questioner found an increase in risk for mania, an increased neurodevelopmental condition load in boys with both exposures. So I wonder if you can comment on that. Mike, can you unmute?
That last sentence, I missed that last part.
So that they found an increase in risk for mania and increased neurodevelopmental conditions load in boys with both exposures. So I think both neurodevelopmental conditions and risk of adversity.
Yeah, it very well might be, and it's a limitation that we have. So we've published the findings on ADHD and depression and also neurodevelopmental multimorbidity. Obviously, we only looked at those 4 conditions. There is definitely other ones that exist. Of course, there is. In Scotland, we've got very good data on, for example, intellectual disability and autism. We've also got very good data on ADHD through the medications. Depression is a little more of a grey area, because obviously if you're prescribed antidepressants, you still may not have depression. You may have OCD or anxiety and things like that. But there is, of course, other things like oppositional defiant disorder and mania and all these different things which we don't have great data on. So it's just a limitation of it. But absolutely, there can be other things in there that are pushing those.
Thanks very much. That's fantastic. So Carol's asked what synthetic data is. Carol, I'm just typing an answer to you. It'll come in. Sandy, we hear that medical data has been sold by the NHS in England to American tech companies and also insurance companies. With AI being such an important and powerful tool, isn't it more important than ever that patients can trust that their health data will remain confidential within the NHS? So I wonder if anyone who has worked with NHS routine data would like to comment on that.
I think so. I work with NHS routine data. I think obviously it's very, very important that we protect people's identities and that data is not sold to the highest bidder. Equally though, I think it'd be a great shame if we didn't use the data that has been generated. There's so much routinely collected data within the NHS, which if it's in a usable format, could inform so much meaningful research and would make some big changes to the way that we practice medicine. So I would hope that the fears surrounding sharing the data doesn't stop people opting into studies and sharing the data.
Yeah, just to, I think one reason that a lot of governments turn to these big American tech companies is because they have more computing power. If you look at Google or Amazon, they've just got thousands of servers for crunching all this data. But I think there are some techniques coming out in this space where you can use what's called transfer learning, where you take a model that's fit to do some task and you sort of just tweak it to do something else. So for example, say if we're getting a computer to read these radiological reports like Heather was discussing, rather than if you start from scratch, you just need millions of records. But if you start with an algorithm that say already knows how to digest news articles, and then you just tweak it, okay, instead of reading the news, read radiological reports. It already understands how sentences are put together and sort of what subjects, and you need a lot less computing power to fit this kind of models. So I think we should be looking at, how can we use these techniques, but do it more locally on the systems where the data already lives.
Mark, yeah, I'd just add to that myself, actually. I think, well, this is maybe going to turn into a question for the rest of the panel too. I think that there's a lot of public concern about data sharing, though in our survey data, we found pretty widespread support for use of routine data and for data linkage as well in a UK-wide sample. But I do think that people are relatively unaware of the kind of process that researchers have to go through before they can access these kinds of data. And, you know, all of my secondhand experience of observing colleagues going through this process has just been that it's sort of agony, months and years of permissions and processes. And I just wondered if the panel had any opinions on the kind of, you know, are there ways to streamline that process and make it more efficient in order to yield, you know, to maximize health benefits and the speed of discovery without compromising on kind of trust and quality of that system?
I think it's a really good question. I think a lot of the reproducible science could sort of help there. That we do get these data sets and they're kind of quite a raw dump, but in a way it feels like just a raw you could think of it like an Excel file, for instance. And it takes a long time to understand how to best process and extract, those kind of records. So if there are a way to look at, say, another Scottish research group and say, oh, they requested this kind of prescribing data and did this kind of analysis, if we could jump on to the point where that group was already at and say, well, let's just add this one extra bit without having to go through all of those previous steps, then it would help. It would help a lot, and also sort of create a little bit more transparency. People could look and see exactly how the data is being used. But I think we shouldn't underestimate the sophistication of patients and people who use NHS resources. We all log into Amazon and do our shopping and use Twitter. People are very used to seeing sort of complex data on their computers. So I think if you could give them insight into where is all my data right now? It'd be great if I could log into an NHS website and see, oh, there's a computer at Glasgow that's crunching my data right now, and this is exactly the question it's working on. We might be able to build a lot more buy-in if people could feel like they can actually see what the process is.
I completely agree. I'm going to change tack briefly before we finish, because there was a question a little while back from Donald McIntyre asking Heather about why the classification algorithm didn't replicate in UK Biobank and whether it was due to overfitting. And Heather, you've posted in the chat, but I just wanted to give you a chance to maybe expand on that answer a bit, if you wouldn't mind.
Yeah, sure. So, I mean, it may well be the case that it's kind of winner's curse, and the problems of overfitting, which are kind of particularly in the imaging field. It's been shown by other studies as well that when you try and replicate and you have bigger and bigger studies, the accuracy just drops off, and that's just something that we all have to be aware of, I think, when we're using these kinds of methods. I mean, that paper is actually published in Human Brain Mapping, and there's various different methods that we've used to apply to the data and try to maximize the algorithms that we've used. And yeah, still the accuracy just dropped off when we tried to replicate.
Mm-hmm. And how much faith do you have in the sort of analysis where you leave out portions of the sample? You might already have done that in that particular.
We did do that already in the sample,
and it's not enough.
No, but I mean, I have to say that I could go into more detail here, but these were just derived phenotypes from the imaging data. We weren't actually using the raw data; they were kind of processed data. So there is more data that's available in there that we're in process of looking at next to see if that helps.
Thanks, Heather. Well, I think we might be bang on time to draw to a close, right? Thank you so much to everyone who presented their work and took part in the Q&A session. Thank you everyone who posted questions and making them, concise and readable and articulate. That was very helpful for me. And thank you to Breda for inviting us all to come together to talk about this. I don't know if anyone has any last words that they want to add.
Well, I just want to thank you. It's been a great session. I hope that the audience have enjoyed it and have seen the breadth of what's going on. I think for attendees who are here who want to follow up with our individual speakers, there is a way through the people menu on the right that you can send a message directly to someone. So that might be something that some of you might want to do during the rest of the afternoon if our speakers are sticking around. Apart from that, I think it just remains for me to say, please go and look at the poster sessions, which are just about to kick off at 2:30. I believe that's also in this session's part of Hopin. And enjoy the rest of the day. Thank you.
Thank you.
Thanks.